Okay, ladies and gentlemen, so I want to do some examples here. So here's an example. Example. You can't see. Okay, good. Where is f of x, which is going to be given by root x plus 1, where is it continuous? So that's kind of an interesting question. I'm no longer giving you a point where I want you to go look at. I want you to be able to look at this function and tell me where it's going to be continuous. So the first thing I do is I kind of look at what the function's being composed of. And I notice it's being composed of this, which is a power function. Thank you, Olivia. So it's a power function, and as we talked about earlier, I didn't have you write it down, but I do think I said it, and it's probably important that you do write it down somewhere. Power functions are continuous everywhere they're defined. So that's root x. Do you remember what that looks like? That looks like this. So root x is absolutely a continuous function anywhere it's defined, and this particular function is defined for all values of x greater than or equal to 0. So power functions are continuous, and I don't really think you should memorize power functions are continuous. I think you should look at it and say, what is that darn thing? Oh yeah, it looks like that. Oh, did I have to lift my pencil at all to draw it? No. So it's continuous everywhere I was able to draw it without lifting my pencil. I think that's your best bet. So they are continuous on their respective domains. And so this one is going to be continuous on x is going to be greater than or equal to 0 for this one. All right, here's another way to say that same thing. And I hope that you're okay with both, because I'm going to jump in between. Okay, so there's two ways of saying the same things. Now what about this? 1 is a constant. So if I was looking at just 1, now believe it or not, 1 is a graph. Think about it. Y equals 1. Set up a table of values. X, 1. No matter what I put in for x, -1, 0, 1, 1, 1, 1. There's your graph. That's y equals 1. Let's not get confused here. Let's know what this stuff is graphically. That's a continuous function, isn't it? This is continuous everywhere. I was about to put a square bracket, but I can't because you can never get to negative infinity. Okay? So it's continuous on that domain. So the question now is, okay, so where is f of root x plus 1? Well, this one is continuous on that domain. This one is continuous on that domain. So they're going to be continuous. This will be continuous wherever they're both continuous. Does that make sense? So the whole thing's going to be continuous on, yeah, that makes sense. I can't be continuous where this one's continuous and where's this one not. That doesn't make sense. It has to be where they're both continuous. Good. If you wanted to do a picture of what this looks like, and I think that's not a bad idea just to really start really understanding, this one, root x, is continuous like this. And 1 is continuous everywhere. So where are the two of them continuous? Both of them get continuous there. And I think that's a good way of thinking about it. That's a graphical approach of trying to visualize what's happening. That's what the solutions look like. That's what all the x values look like. It's not what the function looks like at all. It's what all the domain values that I can put into this function, where it's continuous look like. This particular function looks like this. And we should have an understanding of that. We should have an understanding that this is root x, and that's a vertical shift. And as you can tell, it's continuous everywhere from 0 to positive infinity, which gives you...
So the square bracket means including...
That's right. Yeah, and we have to be very clear on that. That square bracket means the x is greater than or equal to 0. Now, I wrote it backwards. I'm not sure why. I think because I was going to do this. And you guys are funny. Those two mean the same thing. You have to get good at being able to read both of those. And what that means is that. Okay, so I think I've beaten that question to death. We've talked a lot about notation there. Let's look at another one. Where is f of x equals x over x squared plus 5x plus 6 continuous? Okay. Well, we've got to sort of look at what's here. I've got a polynomial on the top. I got a polynomial on the bottom. If I was to graph those, I think we both know this is a line, right? I hope we both know that. I hope we both know that this is a quadratic. They're continuous everywhere. So both are pretty good. The only problem might be where the function has any vertical asymptotes, right? Problem might be where f of x is not defined. And f of x is not defined by division by 0. So if I was trying to talk to someone about this, I'd say, well, okay, well, x is continuous everywhere, right? It's a polynomial function. Yep, absolutely. And I would probably say this, well, that too is continuous everywhere. It's a polynomial function. Now, the problem is f of x is composed of those two. F of x is undefined if we have division by 0. That's a problem. That's a rational function. So, I guess we better find out where that could happen. I'm thinking plus 2 and plus 3. I'm going to check it. X times x is x squared. Yep, it works. So we're going to have a problem when x equals negative 2 and x equals negative 3. Now, notice I'm using equals here. Really, it's undefined for these values. Okay, so f of x is going to be undefined at x equals negative 2 and x equals negative 3. But it's going to be defined, f of x is fine everywhere else. So a graphical representation of the answer, not of the answers, of the possible domain that could go in here is going to be created I cannot put in x equals negative 2. I cannot put in x equals negative 3. But I can have everything up here, everything in here, and everything down here. So how am I going to talk about that? Well, this area is going to be all the values from negative infinity to negative 3, not including. And this area is going to be negative 3 to negative 2, not including. And this area is going to be negative 2 to 0. So I've effectively talked about this, and this in those three. And that's where it's going to be continuous. Now that's a complicated way of saying it. It would be much easier to tell someone where it's not continuous. But that's not what they asked for. They want to know where it is continuous. Oh, thank you. We'll go to infinity. No, excellent. We don't stop at 0. We keep going to positive infinity. Thank you. Good, good, good. Good check. So now I need to let you know something, and I'm not going to go into a big explanation of it, but do you see these ands? You know what that means, right? That means this and that and this. So if I was having a birthday party and I was inviting Joe and Sam and Philomena, whoever I'm enjoying, that and means to include, right? It's kind of like a union of people coming together. Did you hear that? It's a union of people. So in mathematics, we use this symbol. It's the union symbol. and it means that we're going to add those intervals together. So it's the union and the union, which if you've taken any data, you've seen this, and this is in contrast to this symbol, which is intersection. And we're not going to talk about that right now other than to let you know that there is a difference. This is the union, and it means and. And if you put and, that's great. But if you put the union sign, guys, the gals really dig it if you know your terminology, okay? And girls, don't date a guy that doesn't know their math, okay? This is the rule. So guys, you want to impress the ladies, you're going to use the union sign. All right, we're going to stop there and we'll be right back.